Hi, in this video we will perform the encryption of the MySQL server instance files. We can encrypt the InnoDB tables, and under the InnoDB tablespaces we have like files per table tablespace, where each table's data is maintained as a file, and the general tablespace. And under the general tablespace you can have multiple tables data residing on the same tablespace. For both these table spaces, either at the time of creation you can specify the encryption, or if the tables and table spaces are already existing, you can later encrypt them. Also, you can encrypt the MySQL system tablespace. This gets created when the MySQL server is created, and you can alter that MySQL tablespace to be encrypted. Just like files per table and general tablespace have their own advantages and disadvantages, even in the case of encryption also we have the advantages and disadvantages. The files per table tablespace encryption uses a copy algorithm, meaning when we try to encrypt a files per table tablespace, it would need twice the amount of disk space. If the table is of 10 GB, we would need one more 10 GB amount of disk space. It basically creates a new file and copies the data from the old file and writes it encrypted in the new file. Also, you cannot track the progress of the encryption in the case of files per table tablespace encryption. Also, you cannot do DML on the tables. While encryption is in progress, it will obstruct the DML operations. So you'll have to consider that when you are performing the files per table tablespace encryption. Whereas the general tablespace, it's an in-place encryption, meaning it does not create a new file or anything. The same existing tablespaces data file gets encrypted. And while the general tablespace is getting encrypted, you can perform DML on the underlying tables, and even you can track the progress of the encryption operation in events stages current table. That is only for the general tablespace. So let's see that. This is MySQL 9.3 host, same host, where we are having the MySQL 9.3 Enterprise Edition. So we have Sakila database here. So let's try to encrypt a few tables there. I have connected through a client, and this thing information schema.innodb tablespaces shows the details for files per tablespaces and their encryption details. So for encryption column, so far no table is encrypted. Let's encrypt a few tables. We will encrypt store, staff, and rental. Okay, I need to specify Sakila database. Okay, we performed the encryption of 3 tables. Store, staff, and rental, their encryption attribute is now yes. So we have one more table, film text. This is having a full text index and these 2 columns. So these are the files related to the full text index. So once we encrypt the film text table, which is having a full text index, all these files also gets encrypted. So let's encrypt that. As of now, this is not encrypted. Encryption is no for them. So let's try to encrypt that. Okay, So all these files along with the table film text and all the files of that related to the full text index also got rewritten. So film text and the full text index files also got encrypted now. So now let's go for encryption of one of the big table, sample data. While we encrypt this table, we also try to perform a DML at the same time and see it. So before that, let's see the content of the table. The table name is sample data. So we have some dummy data here, user 10 and his email ID user10@example.com. Now while this table is getting encrypted, we will try to modify this email value to a different value. For that I have opened one more session. So this is one more session. Let me get the connection ID for this. This is connection ID 18 and this is connection ID 20. So we will try to encrypt the table. Okay, now I'm all set. Let me try to trigger the encryption now. At the same time, I am also triggering the update on the same table from a different window. If we see in the process list, this is doing 20 is doing copy to temp table and 18 is doing waiting for table metadata log. And meanwhile, if we go here, it has created a temporary file. So while the table is getting encrypted, it has created a temporary file and doing the encryption there. So now it performed the encryption and the update also went through. Once the encryption is completed, then the update went through. Before that, it was waiting for table metadata log. It was waiting. So connection ID 18, we triggered the update there. So it was waiting, and connection or thread ID 20, we triggered the encryption there. There it was doing the encryption operation, and this temporary table would be disappeared once the encryption is completed. So we don't see it now. It got renamed again into sample data.ibd. Now this table is encrypted, so we can see that. It is encrypted. So this way, for files per table space, we need to consider the time that we are encrypting them, because we cannot perform the DML on the tables when they are getting encrypted. Also, we cannot track the progress of the encryption for them. We also have a general tablespace TS1. We will try to encrypt that now. So we have a general tablespace TS1, and under that general tablespace we have two objects or two tables, sample data G, sample underscore data G, and movie underscore actor. When we encrypt the tablespace TS1, both the tables get encrypted, or for that matter any tables in the tablespace, they all get encrypted at the same time. So we will do the encryption of the tablespace in one window, and we will try to perform an update operation on the table which is residing in the table space in another window, and we will see that. Okay, let's perform the encryption of the table space here. All the tables or indexes under this table TS1 will be encrypted when we do this encryption. Okay, we are performing a DML on the sample data G, which is under the table space TS1. Now let's check the status from process list. So both are running. The update is happening, it is not getting blocked. Okay, so thread ID 18 looks like both of them got completed. The table space is encrypted. This is only to show that we can perform the encryption of the table space without the DMLs getting blocked for the general table space. I also wanted to show one more thing to track the progress of the encryption. So I could not show that. Let me again say the encryption as no, and then we re-encrypt again. Next time we will see the progress of the encryption, or here also we can see the progress of the encryption. I am saying the encryption as no, so it should rewrite without encryption now. At the same time we will see the status of the encryption. Okay, now out of this much work it has completed this thing. Okay, now it says it is completed. Okay, it's completed. So we can track the progress of the encryption for the general table space. Just for fun I'll re-encrypt it again. This is not the case with the files per table tablespace encryption. Now it should be done. It is completed. So this way we can do the encryption for the files per table tablespace and the general tablespace encryption. Also let's do the encryption for the MySQL system tablespace. Okay, before that we can see the encryption attribute for the tables. Data G is the table name, so it says encryption is equal to Y now. Let's encrypt the MySQL system tablespace. This is also an in-place encryption. Okay, it is done. InnoDB encryption uses a two-tier architecture, meaning you have the master encryption key in the keyring file, and when you encrypt a table space, the data in the table space will be encrypted using a tablespace key. So this is a tablespace TS1. The data, when you do the encryption, a tablespace key is created for that, and the data in this tablespace is encrypted using this tablespace key. So similarly, if you have second tablespace TS2, it will have one more tablespace key, and the data in this tablespace will be encrypted using this key, and it can only be decrypted using this key. But the tablespace keys themselves are encrypted using the master encryption key from the keyring. Using this key, the tablespace key itself is encrypted, and the encrypted version of the tablespace key is written into the tablespace header. It is written here. So when a user or when the application tries to read from this tablespace, InnoDB gets the master encryption key, uses that master encryption key to decrypt the tablespace key, and once it has the tablespace key decrypted, it can make use of the tablespace key to decrypt the data that is encrypted by the tablespace key itself. So this way it is a two-tier architecture. Also, if you rotate the master key using this statement, alter instance rotate InnoDB master key. If you rotate the master key using this statement, a new key is returned to the keyring. New key is returned to the keyring, and that new key is used to encrypt all the table spaces encryption keys. Each table space has its own encryption key. Using that key, the data is encrypted. So the table space key is also re-encrypted, and the re-encrypted version of the table space is written into the table space header. So for table space 2 also, using the new key from the keyring file, the table space key is re-encrypted, and that re-encrypted version of the table space key is written into the table space header. Also, this is an atomic operation, meaning it should happen for all the encrypted files. Writing the re-encrypted version of the table space key into the table space header, it should happen for all the table space files whenever you rotate the master key in the keyring. Also, one more thing is, when you rotate the master key, no data gets re-encrypted and written. No data gets re-encrypted. The reason is the decrypted version of the table space never changes. So even if you change the master encryption key, the new master encryption key is used, and then it re-encrypts the table space key, and then the re-encrypted version of the table space key is returned to the table space header, but the decrypted version of the table space key never changes. That is the reason why whenever you rotate the master key, no data gets rewritten. It is only the header of the table space that gets rewritten with the re-encrypted version of the table space key. So that is one thing. To encrypt the undo and the redo, we can set these variables. For the redo, InnoDB redo log encrypt is equal to on, and for the undo, InnoDB undo log encrypt is equal to on. And once we set them, from that time any undo or redo that is generated will be encrypted. And if at all there is any undo or redo that was generated before we set, it will remain in unencrypted format. Also, once we run them, the data, the undo data or the redo data will be encrypted using the tablespace encryption key, meaning if we perform a DML on this tablespaces data, the redo page will be encrypted, and it will be encrypted using the tablespace encryption key, and this tablespace encryption key will be stored in the header of the redo log. And the same way, the undo also will be encrypted. The undo page will also be encrypted using the tablespace encryption key, and the encryption key will be stored in the header of the undo log. Now let's set them. Okay. This way the undo and the redo are encrypted. Okay, we can turn on the binary log encryption by setting this variable bin log encryption is equal to on. But before we turn it on, we need to talk a little bit. Binary log encryption also makes use of two-tier architecture. Uses two-tier architecture, meaning From that moment, any new binary log that is getting generated will be associated with a unique password. Binlog1, binlog2, binlog3, and so on. It will be associated with one password, pass1, pass2, pass3, and so on. So this password is used to encrypt the contents of this binary log, and this password is used to encrypt the contents of this binary log, and this password is used to encrypt the contents of this binary log, and these passwords in turn are encrypted using the master encryption key that is stored in this keyring file. A new binary log master encryption key will be generated. Just like when we encrypted a tablespace, a new tablespace encryption key was generated. Similar way, for the binary log encryption, when you enable this by setting this binlog encryption is equal to on, a new binary log encryption key will be generated, and it is written into this keyring file, and each binary log or relay log that is getting generated will be associated with a unique password, and the contents of these binary log files or the relay log files will be encrypted using the unique password. Relay log 1, relay log 1, relay log 2, relay log 3, and password for relay log 1 and password for relay log 2, unique passwords, password for relay log 3, and the passwords themselves are encrypted using this master encryption key that is generated for the binary log, and the encrypted version of this password is stored in the header of the files. So if at all the server has to read this thing, it reads this header, it goes to the keyring, gets the master encryption key for the binary log, uses that master encryption key to decrypt the password. Once you get the password, you have the contents accessible, you can access the contents. So what happens, again here also you can rotate the master encryption key for the binary log. So what happens when you rotate the master encryption key for the binary log? A new key is generated and it is written to the keyring file, and that new encryption key is used to re-encrypt the passwords, and the re-encrypted version of the passwords is written into the header. But the contents are not rewritten, just like the tablespace, right? The contents are not rewritten. Only the header of the files is rewritten with the new master encryption key. The password is encrypted, and that encrypted version is written into the header. So again, it is the same case here. Even though you rotate the master key, the contents are not changed, only the encrypted version of the file password changes. But once you decrypt, the password itself will never change. So that is the reason why the content is not rewritten, but only the header is rewritten. So this is what. Also, so let's set this thing, binlog encryption is equal to on. We know that once we set this to on, it will generate a new master encryption key to encrypt the passwords for the binlogs and relay logs, and that new master encryption key will be written into the keyring file. So the keyring file should be read writable now. Will get an error. Fail to store key. Please check if keyring is loaded, but keyring is active. What is stopping the new binary log encryption key to be written to the keyring is SC Linux. So from a different window, let's check the status of SC Linux. It's enforcing. Also there is one more command, SC status. current mode is enforcing. If it is enforcing, it abstracts writing into the keyring file. So we'll have to disable that. We have seen this thing in the previous video also. So this will disable that, and we will be able to write the new master encryption key for the binary logs and relay logs into the keyring file. Now if we turn it on, okay, there is one more thing I want to show you. Before that, we know that we can see the contents of the keyring's key ID from this table. Only one key is generated now, and that we are using to encrypt the table spaces. So let's set this command again now. Set persist binlog encryption is equal to 1. Now it is able to write to the keyring file. Let's also check the contents of keyring file. Okay, it is just written now. It is just written now. New master encryption key for the sake of binary logs and relay logs password encryption is written there. Okay, this is a encrypted file, password protected encrypted file, so it does not help us much, but we can see the key that is generated here. Okay, now you see the contents. It has generated key, and this key is used to encrypt the passwords. This key is used to encrypt the passwords for each binary log file or relay log file, and the encrypted version is written into the header of the binary log file or the header of the relay log file. So that is the thing. Also, you can see the current binary log is encrypted, not the older ones. The older ones still say the same. From now on, any new binary log or relay log that gets written will be encrypted. Also, this thing stays till we reboot the server. Once we reboot the server, it will again go back into the enforcing mode. That is the reason why it is into enforcing mode. I set this to the set enforce 0 permissive mode in the last video, but then I rebooted my machine multiple times. That's why this thing enforcing is into effect. Okay, moving ahead. From now on, if we want any table space or any schema that gets created to be encrypted, then we need to set a global variable. We need to set this variable, default table encryption. Once we set this system variable, from then any schema or the table space that gets created will get its encryption value inherited from this variable. So let's set this. Okay, I have created a user to demonstrate this. As a different user, Praveen at the later localhost, we will connect with that username and we'll try to create a schema and also a table space without specifying this encryption attribute and see. Okay, on another session, let's try to log in as the Praveen user and try to create a schema and table space and see its encryption values. We are not specifying the encryption attribute for the schema test 1. We are not specifying the encryption attribute for the table also. The schema gets its value inherited from the default table encryption global variable value. So let's try. Okay, this value is inherited from that global variable default table encryption. Now let's try to create a table space. We'll create a table in the table space. Okay, the table which is created under the newly created table space is also created as encrypted. Now we have one more thing, this variable show variables table encryption privilege. By default the variable's value is off. When we set it to on, it will enforce this default table encryption even for the alter statements also. So let's check that, but before that we'll see something. We have created this table space without the encryption value, but it got its encryption attribute from the variable default table encryption. We can see that TS3, the encryption attribute is Y as of now, but let's try to see if we can say it as no as the same user. Prevented the local host. Let's try to alter this table space to encryption as no. It is fine now. The table space got the encryption as no now. But if you want that to be avoided even for the alters, then you need to set this table encryption privilege check to on, so that what happens is even for the alter statements it will go and verify this value default table encryption, and it will enforce that value even for the alters. So let's set that. Okay, so let me try to, okay, so once I set this variable set persist table encryption privilege check is equal to on, even for the alter statements it verifies this variable value default table encryption, and it upholds this value. So it can't modify the encryption attribute for a table space to no. I know it is no already, but still it will work. Let me show you. As a root user I will say it as yes again. It works, but as a user Praveen, if I try to again say it as no, it does not work, because it is enforcing the default table encryption value which is set to on, so it is being enforced now. Also it enabled this root user to modify. The reason is it has got, the root user has got some special privilege. Root user has got some special privilege, table encryption admin. Since the user is having this privilege, he will be able to override the value that is set for the default table encryption. He will be able to override. But if any user is not provided this privilege table encryption admin, they won't be able to override the value set for the default table encryption. Say, for example, if you want this user to modify the encryption attribute, then we need to grant him the privilege. Let's grant it. Okay, I need to specify on the databases. So this is a global level privilege. So grant table encryption admin on star dot star to Praveen @localhost, and let's fetch the privileges. And also in the different session, let's try to relog in. Now if we try to set this as encryption is equal to no, he should be able to do that, because he is also given the privilege to override the default value that is set for the default table encryption. He got the privilege to override that. So the concept is like this: if you want any table space or any schema that gets created to have a default value, then you can set this thing, and once that default table encryption is set, any table space or any schema that gets created will have the encryption attribute inherited from this value, but user can still go ahead and try to modify the encryption as no for the table space. And if you want that to be avoided, then you need to set this variable table encryption privilege check. By default it is off, and if you turn it on, if at all you are trying to modify the encryption attribute, it verifies if it is in sync or in line with this default variable value. If not, it won't allow. But if you want this thing to be overridden, table encryption privilege check to be overwritten, then you need to grant this privilege, table encryption admin. And that completes this video. Thank you for watching.